For part A, from the given problem statement, a diagram is drawn. Several assumptions were made, such as that this problem is covering transient mass diffusion and that the diffusivity coefficient is constant. Properties were derived for the helium-pyrex diffusivity coefficient from table 14.3. After writing the correct equations, a solution was created. The Rasengan is still intact after 1 minute, as the helium has diffused less than 3 millimeters. For part B of problem 3, after the given problem statement, a similar diagram to part A was drawn. Part B covers learning objectives 5C and 6A. Several assumptions were made, such as that the diffusivity coefficient is constant and not time-dependent, densities are constant, and this problem covers steady-state mass diffusion, and this can also be reflected by one-dimensional mass transfer. Similar properties to part A were calculated. However, different equations were used. As everything was given to us within the problem statement, the diffusivity coefficient, or the flux, was calculated. In part C of problem 3, from the given problem statement, a diagram was drawn. However, this diagram differs from the other two as it has a different base of problem. We are asked to find the length of the tubular membrane, as this problem covers learning objectives 8B. We can assume that the selectivity of nitrogen is much greater than oxygen, which means it is infinite. The properties of the tubular membrane are given within the problem statement. After writing down the equations, variables were plugged in, and the area was solved for. From the area, we can determine length of the tubular membrane. Created problem number 4, which covers learning objective 8A. This problem covers an incorrectly installed heat exchanger, which turns a counterflow heat exchanger into a parallel flow heat exchanger. After a diagram is drawn and labeled from the given problem statement, several assumptions were made, such as steady-state operating conditions, that the heat exchanger is thoroughly insulated, which means no heat loss, fouling is negligible, as it is a one-shell, one-tube pass, constant properties of flow rates, thermal resistance due to pipe wall is neglected, which means no fouling, original design dimension of original heat exchanger, the countercurrent one, remains the same, water properties at 56 degrees can essentially be reflected by the water properties at 55 degrees Celsius due to the 1 degree Celsius change, and a correction factor for log mean temperature difference is equal to 1 due to the one shell, one pass assumption. Given properties at 55 degrees Celsius were found. After writing down the equations, everything was plugged in and solved for. From the original heat exchanger, the countercurrent one, an overall mass coefficient could have been found. That mass coefficient, or overall heat transfer coefficient, was plugged into the overall heat transfer rate equation for the parallel flow, and the heat transfer rate for the parallel flow heat exchanger was calculated. In part B, it asks us to analyze the pipes before the heat exchanger. This covers learning objective 7A. From the problem statement, we are able to draw the diagram, and several assumptions are made, such as steady-state operating conditions, liquid flow rate is fully developed in the tube, only internal force convection contributes to the heat transfer rate due to the thin wall approximation, as negligible thermal resistance of the wall thickness. Several properties were calculated at the temperature of the bulk of the fluid, which was calculated from the equations below. After writing down the equations, everything was plugged in and solved for. From the temperature of the bulk, the properties of the water were discerned and plugged in to the heat transfer rate equation. The condensation rate was uncalculated. In part C, we are asked to analyze the pipes that exit the heat exchanger. From the given problem statement, we are able to draw a diagram. Several assumptions are made, such as steady-state operating conditions, thin wall approximation, negligible thermal resistance due to thin walls, natural convection is the only mode of heat transfer that contributes to the heat transfer rate, and the surface temperature is the same as the pipe flow temperature, due to the thin walls. Properties at the temperature of the film, which is calculated below, were generated. After writing down equations, everything was plugged in and solved for using the properties, as well as various equations, such as Rayleigh's number instead of Reynolds number to make sure the rate was okay, as well as Nusselt's number, which was then used to calculate the heat transfer coefficient of the average of the pipe. Created problem number 6. Created problem number 6 covers learning objectives 7D for part A. From the given problem statement, we are able to draw a diagram. Several assumptions were made, such as pressure is at 1 atm within the pressure cooker, properties are constant of the water, steady-state operation can be assumed, not steady-state though, which is different than steady-state operation, and the temperature of the surface or the bottom of the pressure cooker is equal to the temperature of the hot plate. Properties were calculated for Tsat, which is 90 degrees. Equations were written more specifically the equation for the nucleate boiling heat flux. Properties were plugged in, and the nucleate boiling heat flux was solved for. In part B, which covers learning objective 7b, from the problem statement, we are able to draw a diagram. Several assumptions were made, such as surface temperature of the water is 90 degrees, as water is initially uniformly at 90 degrees, which is why the assumption can be made. Steady operation can be assumed, but not steady state, which is different. Air is an ideal gas. Constant properties of air and water can be assumed. Pressure is also equal to 1 atm. Heat transfer is only due to external forced convection and fully developed laminar airflow, which is then proven on as we calculate the equations. Properties at the temperature of the film, which is calculated below, were derived from tables. These properties had to be interpolated due to the 52.5 degrees Celsius temperature of the film. Equations were written and solved for using the properties. After calculating the average heat transfer coefficient, it was plugged into the heat transfer rate of just the convection, and the heat transfer rate due to convection was found, due to forced external convection was found.